Okay, good morning. You've got the weekend to finalize your design project demand estimations, and I've been getting some good questions in my office that make it clear. At least some people in the class have gotten a good head start and are kind of reasoning through. You know, the toughest thing on a project like this is just getting started, and sometimes you feel uncertain about how to get started. So I'll give you a hint that you need to begin by calculating the area of the north zone, the south zone, the east zone. So that's how to get started, is find what is the area of those three locations, and then the demand estimations kind of take off from there. So I previously went through some of the characteristics of a good quality submission, and if you missed that, then the video is included in last Wednesday's, well, I guess it was this Wednesday, 2 days ago, the lecture video that's on YouTube. You can re-watch that and just refresh your memory on what makes something a good submission for the demand estimation. Homework 8 is still a week off in the distance, but if you want to solve that now, probably some of these concepts, while they're still fresh in your mind, will be easier to solve the homework problem sooner rather than later. So we're going to continue on some additional topics from Chapter 11 today, talking about channel efficiency and shear stress and how that relates to the resistance that water encounters as it's moving through a channel. But before that, I wanted to remind you about the career fair, which is coming up next week. And I recently looked through the list of employers, and there's at least 20 companies coming, construction companies, engineering firms, agencies, at least 20 that are going to be looking to hire civil engineering interns and graduates. So this is really a golden opportunity. Even if you have an internship lined up for this summer, it's still good to check in and see who else is really anxious. Not to say that you'd want to necessarily ditch out on your current internship, but if you're going to be graduating and looking for work anytime in the next year, which is I think most people in here, this is a great event. And you know, even if you already have a great offer and you're all lined up for work, it's still good to network and see, you know, who are the people out there that maybe are alumni or doing work in the area. So this is a great event. You'd be crazy not to attend this. And so my recommendation is, you know, polish up your resume and include any new software or skills or experience that you've got. And if you need somebody to look it over, the Office of Career Education has a service through Handshake that you can do that. I'd be happy to look at it if you want me to look at it. Then go to the career fair, maybe a little bit more dressed up than normal. I mean, you don't have to wear a tie and a jacket and a suit, but if you wear something a little bit more upscale than a t-shirt, then that's probably going to help you to feel more comfortable while you're there. So you should go to the career fair. I'll be going over there, and I'm not even looking for a job. I'll be going. Yeah?
Could we possibly not look at hydraulics or hydrology?
Hydrology? Well, that's 1 hour out of 4, so if...
Well, because after hydrology we have to do our presentations for capstone.
Mm-hmm.
I don't know if we have to meet for capstone class that day as well.
Yeah. Well, you know that I record my lectures, and so I'll let you make the choice. I don't anticipate, I mean, I don't know when quizzes will be in that other class, but nothing on the immediate horizon. All right, so let's talk about water flowing through channels. When it does, remember we've talked about how there's some energy losses. It's not energy loss due to pipe friction, because this isn't flow through a pipe, but it's energy loss due to friction of the water flowing over the surface of a stationary solid material. And so in this picture, it looks like we've got some areas that are rock, and they're probably not going anywhere, not just with normal flows anyway. And then in this part of the picture, it looks like there's some granular material, like maybe cobblestone and soil, and that doesn't look as stable as some of the other rock is in the short term. So the reason I bring it up is that remember that when water is flowing downhill, the solid materials that aren't moving resist the movement of the water. So they're pressing against the water in the opposite direction of flow, but then the water is also exerting a shear stress on the soil. And sometimes the shear stress of that flowing water is enough to dislodge the soil, to carry sediment downstream. And one of the ways that we can understand that process is by calculating the shear stress that's applied to the soil. And so the shear stress is a function of the unit weight of the fluid. And so gamma of water is 9810 newtons per meter cubed. And the slope of the channel is something that we can just go out and measure or estimate. You know, you could do a survey, you could look at GIS data, or if you have streams in a certain region that fall within typical ranges of slope, you could estimate it to try and determine what is going to either be the shear stress that's applied by the fluid to the solid materials, or if you know the geometry of the channel, so the hydraulic radius, remember, it's a function of the cross-sectional area, the wetted perimeter. So if you know the geometric details, then you could calculate the shear stress that's being applied to the soil, and then geotechnical analysis would tell you what's the maximum allowable shear stress before the soil starts to be scoured and moved downstream. So we can do really simple estimates of the risk for hydraulic scour in this way. And so if you know the maximum allowable shear stress and you know the slope of the channel and then the hydraulic radius based on how wide the channel is, its shape, like if it's prismatic and trapezoidal or if it's irregular, you can calculate the hydraulic radius. And then once you know the tolerable channel geometry based on a given slope and shear stress of the soil, then you could substitute the hydraulic radius into Manning's equation and then find out what's the maximum allowable velocity. So the speed of the water as it's flowing through the channel, if it exceeds a certain velocity, then that would mean it's applying too much shear stress, and then that means that there's scour occurring. So just as an illustration of how this fits together, what we could do is we could say maybe through geotechnical testing, we've determined that soil has a maximum permissible unit tractive force of 10 newtons per meter squared. And then beyond that, the soil is going to come loose and be carried away by the fluid. So what if we wanted to calculate what's the maximum velocity that would be allowed if this is going to be put out on a 1.5% slope, and then we know the end value of the channel is 0.02 because it corresponds to natural earth, which is straight and in good condition. So we could start by rearranging the shear stress equation for hydraulic radius. And so it's the shear stress divided by the unit weight times the slope of the channel. So for 10 newtons per meter squared and a unit weight of 9810 newtons per meter cubed, and then the slope of 0.015, because remember we have to express percentages as a decimal when we're putting it into Manning's equation or into the shear stress equation. What that tells us is that the hydraulic radius that corresponds to this is 0.0680 meters. Now, into Manning's equation, it is 1 divided by n, so 0.020. Substitute in the hydraulic radius, 0.0680 meters to the 2/3 power, and then the slope of 0.015 to the 1/2 power. So the velocity here would be 1.02 meters per second. And any velocity beyond that is at the risk of causing scour of the channel. Anything below that, then it's not imparting more shear stress than is allowable. So we'd seen this shear stress equation before, but I wanted to just point out that we can combine it with Manning's equation to find out maximum allowable velocities. Any questions about that? Now, on the subject of velocity, one way that we can make physical measurements of velocity in a channel is with devices that you dip down into the water, and you can see that this looks like a propeller. Really what it's doing though, it's not moving the water, but it's being moved by the water. And so this device would have sort of a calibrated understanding between how many RPMs this little impeller is doing, and then on the digital scale it would tell you either how many meters per second or how many feet per second. And you can notice that there are markings on the side so that they could measure at certain depths and know what's the velocity profile. And way back in fluid mechanics, you learned the idea that when you've got water flowing through a channel, so let's say here's the bottom of a channel, and the water, here's the water, and it's flowing this way, that at the bottom of the channel where the water's in contact with the stationary solid material, the water velocity is 0 because of the no slip condition. And so there's no velocity there, but it's a little bit faster up above and faster. And the further away you get from that boundary, the velocity is increasing. And so there's a velocity profile. So we could use a device like this to measure the velocity profile. But sometimes it's not convenient to do that. Maybe you don't have a boat. Maybe you don't have the time because it could be a really wide channel and it could be deep. You know, these don't have infinite length to them. So there have been different ways over the years to try and estimate what the shape of that velocity profile looks like. And one of them that has been put together, it's in our book, relies on the von Karman constant. And this is a pretty complicated empirical equation that is a way of starting off with the average velocity. So this capital V here is the average velocity. And then based on what is your distance from the bottom of a channel, so Y in this equation is the distance, how far up are you from the bottom of the channel, and then D is the overall depth of flow. So inside this logarithm is the ratio of your depth at a certain location to the overall depth, and with the slope of the channel and this von Karman's constant, then this is just a way of estimating what is the velocity at that given depth that you're interested in. And so this has been plotted to show at a couple of different slopes how it does give you kind of a curved velocity profile. When you get really close to the bottom of the channel, this equation isn't really effective at reaching that 0 point. So you see how it's actually predicting a negative velocity once you get into the really shallow range. So you'd need to override this equation at the end and just note that it eventually reaches 0 and it's not going to go into a negative flow velocity. But in any case, it's one approach for creating kind of like a trace of what that profile would look like. And other empirical rules of thumb that have been developed is that in a lot of cases what you might find is that if you measure the depth using something like this, if you go down to 0.4 of the overall depth, so this is saying if you measure the velocity at 0.4 of the depth, so 40% of the way up from the bottom, then that often corresponds to the average velocity. That's just one rule of thumb that our book introduces. Another it says is that sometimes what you could do to determine the average velocity is measure it 20% of the way from the bottom and then 80% of the way from the bottom, and the average of those two would give you. So these two equations are doing the opposite thing. This equation, the one on top, is telling you what is the velocity at a certain depth based on the overall average velocity. But then these are saying, if you know the velocity at a location, how do you find the overall average velocity for the entire depth of the channel based on that point location? So these two would be used if you did have data from one of these, or you otherwise knew what is the depth at a certain, what is the flow velocity at a certain depth. This equation would be if you know the average flow velocity and you want to estimate the velocity at a given depth. So any questions? Okay, so far when I've been showing you a couple of simple trapezoidal channels and we've been solving for the depth, we've used the same n value for the whole channel. And what we've assumed, for example, was maybe it was an asphalt-lined channel. And so we were saying there's asphalt on both of the sides and asphalt on the bottom. But sometimes water is flowing out of the normal channel and it gets out onto the floodplains and it's in contact with hillsides. And in cases like that, you may have a main channel that is lined with concrete or has riprap or maybe grass lining on the bottom. But then when the water gets into the floodplain, we have a lot of variety and irregularities in what materials the water is encountering. And so it could have a very different n value. Let me show you a video that I took 3 years ago when there was some flooding here in Huntington. I was flying my drone out by the park. So if you've ever been to the riverfront park there, you know that ordinarily these trees aren't submerged in water. The water levels were a little bit higher than usual that day. Normally this garbage can isn't underwater, the bathroom building there not underwater, flagpole not underwater, statue not underwater. Water levels were really high. So high, in fact, that they brought out the gate to the flood wall. At least a couple of slats they put into place. You'll see it in just a moment. So there's an opening in the flood wall, which is how you get into the park usually, but the park was closed and they erected this frame to hold the slats in the flood wall gate, and they started putting in a couple of those so that if the water levels got high enough, then it wouldn't spill into the streets of Huntington. I don't think it ever actually touched the floodgate that day. Did anybody go and look at it? Anybody remember this particular flood?
I don't think it got me higher than that.
Yeah, I went and looked a couple of times, and it was never in contact with the gate. But I guess maybe as much as anything, they put this up just so that people wouldn't go drive into the water and make a fool of themselves. You know, there's never any shortage of people who will drive into standing water. So the point is the river. I think I've got a looking down the. Okay. So here is the Ohio River. We're looking into the sun, so it's kind of a little bit hard to see, but the main channel would be carrying quite a lot of flow. The bottom of it is probably a smooth silt. But then in the sides, where all these trees are and benches and stuff, the n value is completely different. And if the water level rose even further and it got into like the city part, then that would really make it complicated to calculate the n value. But the Horton-Einstein method is a way of estimating a composite n value based on all of the parts. And it's effectively a weighted average. So what this Horton-Einstein method says is that the important factor when it comes to n value is the wetted perimeter. So if you know, for example, that this is brush, this side segment up above the floodplain is brush, you could find the n value of component 1 and its length. And then if you knew that this floodplain is maybe a crop like fallow corn, you get an n value associated with that and determine the length of that segment. So likewise, for each one of these numbered elements, what you'd do is you'd find its corresponding n value. You would determine the wetted perimeter, in other words, the distance associated with that. And then what this is saying is the way you average is you'd multiply the wetted perimeter by the n value and add together all of the elements. And then denominator here, you would take the, add together all of the lengths. And then you would have taken the n value to the 3/2 power when creating the calculations for the numerator, and then the sum, all of it together, is to the 2/3 power. So that area weighted average, or well, perimeter weighted average is just been observed to be more accurate than, for example, like a simple average, where you're not taking into account the distance over which each one of those n values applies. So that's how you'd find a composite N value. Does anybody remember how we change Manning's equation when it's U.S. customary units? 1.49. Yeah, so here where it says 1, that's for SI units. But if you were given customary units, feet, inches, and so on, cubic feet per second, then that changes to 1.49. Okay, so if we have a fixed area, roughness, and slope, how do you maximize the flow rate? And so look at these different channels. What do they all have in common? They're all rectangular in shape, but what else do they have in common? They have the same area. Yeah, exactly right. So 2 by 10 is 20 square meters. 2 by 10 is 20 square meters. Do you think that the water would flow through this channel at the same rate as this channel? No? You're right. No is the correct answer. Why not? Why wouldn't it flow through this channel at the same Q as that one? Even though, I mean, it has the same area, right? So wouldn't it have the same flow rate? If they both have the same N value, let's say it's concrete for both of them, and same slope, and same area, different wetted perimeter. Good. This one would have more frictional contact because the wetted perimeter is 22 meters, and it's the wetted perimeter that applies the resistance, whereas this only has 14 meters of wetted perimeter. So how do you maximize the flow rate through a channel? You minimize the wetted perimeter. So we're going to look at that just with a quick spreadsheet comparison of, for these different channels, what is the flow rate that would arise for each of them. So let me just paste this into a spreadsheet, and then what we'll do is we'll calculate what flow rate could we expect for the given 1% slope and 0.013 N value. Okay, so the slope here is 0.01. The N value is 0.013. And then let's have a variety of widths. So B, of course, means the bottom width of the channel, which, since these are rectangular, it's the same as the top width. But we've got B, we're going to define. Y, area, wetted perimeter, hydraulic radius, and then Q in terms of cubic meters per second. Okay, so we have one of these which is 2 meters wide, then 10 meters wide, 5, and 4. Okay, so the depths were 10, 2, 4, and 5. And now the area is just the product of these two, so it should all be 20 for each of these, should be 20. The wetted perimeter, if it's rectangular, it's the bottom width plus 2 times the depth. So perimeter is the bottom width plus 2 times depth. Okay, so we've got the wetted perimeter for each of them. Hydraulic radius is area divided by a wetted perimeter. Okay, and then finally, let's calculate the flow rate. So it is the area to the 5/3 power times the slope to the 1/2 power. Oh, you know what? I need to anchor that reference up to the slope since I'm going to be dragging the formula down. So slope to the 1/2 power, and then all of that is divided by the N, anchoring that reference so that I always refer to that particular cell, times the wetted perimeter to the power of 2/3. All right. So 144 cubic meters per second for this really weird, skinny but deep channel. This would be tough to make too. If you were in the construction business, a channel that's 10 meters deep and 2 meters wide, it's going to be a nightmare. So which of these gives us the most flow rate? It's the one with the least wetted perimeter. So if you minimize the wetted perimeter, that's the one that gives us the biggest flow rate. But the question is, what's the absolute most efficient? Like, efficiency is maximize the flow rate and for the same cross-sectional area. You know, like if you pay excavation in terms of volume of soil removed, if that's the cost of the channel is the excavation costs, then all of the areas have the same excavation cost, but how could we maximize the flow rate? It turns out that it's the half square. The shape that is half square is the most hydraulically efficient, that would give us the biggest flow rate. So let me erase the whiteboard here. And a half square is one where the area is 2 times y squared for a half square. You know, like a half square means that we've got some flow depth and the width is 2y. That's how we can minimize the flow, the wetted perimeter, if it's a rectangular channel. So here, if the area is 20 meters squared, then that turns out that the flow depth that would give us the most flow rate is a depth of 3.16 meters. And so then what would be the width of that? So that would mean that we have to have the width be double that, because the width is 2 times y, so that is 6.32 meters. So let's put that in here and just see. If we have the width is 6.32 meters and the depth is 3.16 meters, so you can see that the area is real close to 20. This wetted perimeter is less than the smallest one we've seen so far. So that gives us an idea we're on track to have the maximum flow capacity. And sure enough, that calculated flow area is greater than the previous maximum that we saw. So we'd call this the best section, or the most efficient. And our book has some formulas for like what's the most efficient hydraulic section for a variety of shapes. So for example, here's the trapezoidal channel that's the most efficient. So the most efficient trapezoidal channel is the one that has side slopes where t is square root of 3 divided by 3. So it's pretty steep side slopes. And the area is square root of 3 divided by, or multiplied by y squared. So it turns out that this most efficient trapezoidal channel is the one that it minimizes the wetted perimeter by being the shape that's most closely approximating a half circle. So that's why it has that particular shape, is it's the one that comes closest to a half circle, which is the way to minimize wetted perimeter for a given area. So that's the best trapezoidal channel. And then here's a table of other most efficient shapes. For example, if you have a triangular section, then it's a half square, but it's a half square on its side. So it is this kind of a half square. Let's see. No, I guess it would be a little bit wider than that. There we go. Half square. So 90-degree angle would give you the most hydraulically efficient triangle section, and semicircle, parabola, and so on. So keep this handy in case you have problems that are asking about the most efficient channel. That means How do you maximize the flow rate for a given cross-sectional area? So, for example, if we wanted to have the best triangular section, then what would be the depth for that? I'm going to pause for a second and see if you can apply this idea. We've got a flow rate of 2.5 cubic meters per second, and we're going to put it into Manning's equation to find the depth. But what you're going to do in Manning's equation is you're going to write the wetted perimeter and the area in terms of y, because we want to know what is the flow depth for this triangular section. And so the unknown here is, what is the depth, where you're going to be using Manning's equation, area to the 5/3, slope to the 1/2, n value times the wetted perimeter of 2/3. So this set of equations for the triangle, instead of a, you'll just put y squared. Instead of p, you'll put 2.83 times y. And then solve for y, where we know the flow rate, we know the n value, and the slope. Okay, the best triangle, the area is y squared, wetted perimeter 2.83 times y. Substitute those variables into Manning's equation along with the given flow rate, roughness, slope. When you put it into your solver, you should get that the normal depth is 0.851 meters. Anybody else get that as well? Yeah? Okay. Krista? You're good? All right. Any questions before we move on? Okay, if there are no questions, then let's look at one more trapezoidal channel. And I put a template file onto Blackboard shortly before class. So if you have your computer, go to Blackboard, let's download that template file and kind of get some additional practice solving a trapezoidal channel using a spreadsheet. So Wednesday you got some practice doing it on your calculator. Hopefully you've done it since then till now. And then let's also do it from the template file. So go to MyMU. It should be in that templates and Excel spreadsheets folder. Excel templates. Normal depth trapezoidal channel. Okay, download that. All right, so here the problem statement is just pasted right into the file there, so we don't have to toggle between the two. Here, does anybody recall why we've rearranged Manning's equation like that? I mean, this is what Manning's equation normally looks like. Why rearrange it this way? Matthew, I bet you know. I put you on the spot, but that's what I do. No? Anybody remember why we rearrange it this way?
So we can find the difference between the left hand and right hand.
Yeah, good. It's because we're going to compare the left-hand side and the right-hand side. And what is it about the right-hand side that's different from the left-hand side? Like when we don't know the flow depth, then everything on the right-hand side is a constant. So the n value is going to be given, the flow rate is given, the slope is given. So we put all of the constants on one side, and then all of the terms that are a function of the depth on the left side. And we'll play around with what y value makes it so that the two sides are equal. Okay, so let's put in what we know about this channel. The n value if this is grassy, and it says in the statement here at 0.035, so 0.035 for a grassy channel. The slope of the channel. Now, this S that we put into Manning's equation, it's not referring to the side slope, it's talking about the bed slope. So for 0.75%, then that means it's 0.75 divided by 100, or in other words, 0.0075 for the slope. The flow rate, we're going to be passing 21 cubic meters per second through the channel, and we want to find out what's the corresponding depth for that given flow rate. We see from the diagram that the bottom width is 2 meters, and then the side slopes are defined as 1-to-1 side slopes. So that's the horizontal is 1 unit, the vertical is 1 unit. And here, T refers to the horizontal component when 1 is the vertical. So my favorite thing on exams is to flip that around and like to define the side slope strange. So be on the lookout for that trick. I'll just be trying to trick you, but you'll remember today's class and you won't be thrown off by that. Like if I said that the side slope is, what if I said something goofy like it's 1 to 0.5? Then what is T? Well, T is not 1. T is 2 in that case because it's 1 to 2, right? So that's the kind of trick I like to pull in exams, just to make sure that you're paying attention. But here in this case, T is 1, and so the right-hand side of the equation is N times Q divided by slope to the power of 0.5. Okay, so the right-hand side is a constant. Now, our depth, we don't know what the depth is, so let's just start off with the depth of 1 meter and then take things from there, see what that gets us, go a little bit further as needed. Okay, so if the depth is 1, then what is the area? Okay, for a trapezoidal channel, area is B plus T times Y times Y. Okay, B plus TY times Y. And we don't need to anchor anything because I'm not going to be dragging this formula down. So if it is 1 meter deep, then the area is 3. And we have to, let's just do a reasonableness check. Does that make sense? If we have 1-to-1 side slopes, and we have a depth of 1 meter, and this is 2 meters, so then that would give us 2 square meters in the rectangular portion, and then 1 meter by 1 meter, so 2 triangles that we add together. So yeah, that is, area is 3 meters squared. So it's set up correctly. We have confidence that this area is giving us something reasonable if we can verify it with pretty easy to calculate depth and area. All right, what about wetted perimeter? So wetted perimeter is, okay, I'm going to embed the calculations for W in here. No, I don't want to do that. That'll make it complicated. I'm going to add another row, and here's W. So if you just right-click and add another row, let's calculate W so that then we can refer to W when we're calculating B. So W is 1 plus T squared to the power of 0.5. 1.41. So that's the square root of 2. Yeah, that's good. All right, so now P will just simply be B plus 2 times Y times W. Okay. Now, finally, the left-hand side of the equation is a to the 5/3 divided by wetted perimeter to the 2/3. So, area to the power of 5/3 divided by wetted perimeter to the power of 2/3. Area to the 5/3, wetted perimeter to 2/3. Okay. What did I do wrong? I missed an extra parentheses in the denominator. Let me fix that. I need one more set of closed parentheses. All right. So this depth isn't right because the two aren't equal. So I know my goal is for the area divided by the area to 5/3 divided by wetted perimeter to 2/3 should be equal to this. So I can do manual goal seek by just gradually increasing the depth until I reach that target, or I can do it in the automated way through the data tab, what if analysis, goal seek, and my goal is for this cell. Oh, I clicked on the wrong thing, I think. Goal seek. My goal is for this cell to be 8.487049. In other words, the value of the right-hand side of the equation by changing depth. So, okay. And it goes and finds that the depth is 2.03. 2.03 meters would be the flow depth that gives us that flow rate for the slope, for the grassy channel, and for the one-to-one side slopes as well. So we're getting pretty good at solving Manning's equation with trapezoidal channel. You should be able to do it with your calculator or with the spreadsheet. You need to be able to do it both ways. That is all the time that we have. Remember that your weekend is going to be a great weekend of demand estimation. And I'll be checking my emails through the weekend if you have questions. Feel free to reach out. Of course, it's a lot easier for us to have a conversation today. So I'll be in my office until 5 o'clock today. If you want to stop by between 2 and 5, feel free. If you've got questions, I'd love to talk to you. So I'll see you Monday.